Okay, let's unpack this. So if you're building software today, I mean, whether it's a simple app or some massive system, you eventually hit a wall, right?
Oh, absolutely.
Writing code that works is, it feels like the easy part.
It is. The really hard part is writing code that survives time, that survives changing demands.
And modifications, which are
It's
inevitable.
exactly. We call that failure mode software entropy. It's this tendency for systems to just degrade and become fragile over time.
And the sources we're looking at today, they really dive into what separates that messy code from, well, truly resilient architecture. They call this a must-know skill.
For sure. And that foundation is called solid.
Right. We are
Yeah.
diving deep into this really powerful set of guidelines for object-oriented design, or O.
And our sources describe solid as not just a set of rules, but really a system for managing complexity before it manages you. It's about building a predictable structure.
What's fascinating is that the acronym itself is a kind of roadmap.
It is. Each letter gives you a different but complementary strategy to fight that entropy, to build a reliable structure that can handle new features without the whole thing collapsing.
So our mission today is to break down each of the 5 principles, S, O, L, I, and D, to understand not just what they are, but why they matter so much for stability.
And how they all kind of interact with each other.
Let's start with the S, the Single Responsibility Principle, or SRP. Now, on the surface, it sounds like simple common sense. A class should have one responsibility.
Hmm.
But I think the common misconception is that this just means keep your classes small.
That is the classic misunderstanding.
Yeah.
Size is a symptom, not the principle itself.
Uh,
The source material tightens that definition up immediately by focusing on change. The real definition is that a class should have one and only one reason to change.
One reason to change.
That's the critical test.
So we're not counting lines of code or how many methods it has. We're counting what? Outside pressures?
Exactly. You're counting the number of distinct external actors or requirements that could force you to open up that file and edit it.
So if two totally different things, like say a user interface change and a database rule change,
Yeah.
could both force me to edit the same class.
You've violated SRP. That class is serving two masters.
Can you give us a concrete example of that?
For sure. Think about a class in an HR application. Let's call it Employee Manager. And let's say this one class has methods to calculate employee salary and methods to generate a PDF report.
Okay, I see where this is going.
If the tax laws change, you have to modify that class to update the salary calculation.
Right.
But if the HR department wants a new logo on their report, you also have to open and modify that exact same class.
And that's where the risk comes in. You change the report layout, and you might accidentally break the tax logic.
Precisely. The solution under SRP is to separate them. You'd have a salary calculator class and a report generator class.
And each of those would then have high cohesion.
Exactly. High cohesion. Everything inside that one class is related to its one single purpose.
Which is the exact opposite of that architectural nightmare, the God object.
The God object. The ultimate violation of SRP. It's that one class that tries to do everything, and it becomes, frankly, terrifying to touch. Focus components are manageable components. That's the lesson.
And here's where it gets really interesting, connecting those focus components to stability. Let's move to the O, the Open-Closed Principle, or OCP. The definition is a bit of a paradox, isn't it? Software entities should be open for extension, but closed for modification.
It sounds like a contradiction, but it's really the core principle for building stable software. So open for extension just means you can add new functionality by writing brand new code.
Okay, that part's easy enough, but closed for modification, that sounds strict.
It is. It means once a piece of code is written, tested, and shipped, you should never have to change its source code to add a new feature. You don't tinker with the internals, you attach something new to the outside.
So why go through all that effort? Why not just edit the existing code? It seems faster.
In the short term, maybe. But the cost of ignoring OCP is huge. Every single time you modify existing tested code, you risk introducing regression bugs.
Things that used to work suddenly don't.
Exactly. OCP minimizes changes to your stable core, which dramatically reduces your testing burden and just increases overall stability.
So how do you actually do this? What are the mechanisms for this plug-and-play architecture?
It really all comes down to abstraction.
Mm.
The sources point to a few key tools here. First, we use interfaces or abstract classes to define a stable contract. That contract is the closed part.
Meaning the system only cares about the contract, not the specific implementation details.
Precisely. The open part comes from inheritance or composition. If you need a new feature, you just create a new class that implements that existing interface. The core system, through polymorphism, can now use your new thing instantly without any changes to itself.
Like a payment gateway.
Perfect example. If you have an iPayment gateway interface, you can add PayPal, Stripe, whatever, just by creating new classes that implement that interface. The checkout logic never changes, it's closed, but the payment options are open.
So OCP is really a risk reduction strategy.
It absolutely is. You decouple the stable core from the volatile details.
Okay, moving on to the L, the Liskov substitution principle, LSP. This one is named after Barbara Liskov.
Right, and the sources say this is the fundamental rule that inheritance must follow.
The core idea is that any subclass has to be substitutable for its superclass without breaking anything.
That's it. It's a check on behavioral consistency.
But wait, isn't that just how inheritance works anyway?
Structurally, yes, but behaviorally, often no. LSP is about the behavioral contract. If you have some code that works with a superclass object, you should be able to swap in any of its subclass objects, and the program has to run exactly as expected. The client code shouldn't even know a substitution happened.
So the subclass can't do anything. Surprising. It can't violate the promises made by the superclass.
Exactly. The classic example that breaks this is the square extending a rectangle.
Right, because a square is a rectangle, mathematically.
It seems fine, right? But a rectangle class probably has separate setWidth and setHeight methods.
Ah, I see where this is going.
If you call setWidth on a normal rectangle, you expect the height to stay the same.
Well, of course.
But if you substitute in a square subclass to maintain its squareness, setting the width to 10 must also change the height to 10.
And that violates the expectations set by the parent rectangle class.
It breaks the contract. The client code is now broken because it got a surprising side effect. The square is not safely substitutable for a rectangle, so it violates LSP. It's about trust in the contract.
Next up is the I, the Interface Segregation Principle, or IST. This feels like it's related to SRP, but for interfaces.
That's a great way to put it. They are definitely linked. The goal is small, client-specific interfaces. The sources are really clear. Clients should not be forced to depend on interfaces they do not use.
So if there's a big interface with 20 methods, and my class only uses 2 of them, why is that a problem? It just feels like a little clutter.
It's way more than clutter. It introduces unnecessary coupling. Imagine one giant iMultifunction tool interface. If 3 different clients use it, but each only needs a few methods, all 3 are now tied together through that one huge interface.
So what's the consequence of that coupling?
If a method that your client, let's say client A, doesn't even use, if that method's signature changes because client B needed it to, client A might still need to be recompiled and retested for no reason.
Because its code depends on the whole interface, not just the part it uses.
Exactly. ISP says to break that big interface into many smaller role-specific ones.
The sources had a great example for this, the robot.
Yes, the example of forcing a robot class to implement an eat method.
Right.
If the robot has to implement a creature interface that includes walk, talk, and eat, the robot has to provide some weird dummy implementation for eat. A robot doesn't eat. It creates a dependency on an irrelevant method.
You should have smaller interfaces, like iMovable and iConsumes food.
Precisely. It's all about minimizing the blast radius of a change.
Okay, finally, we get to the D, Dependency Inversion Principle, DIP. The sources say the goal here is to convert bad dependencies into good ones.
And this one is often the most profound, architecturally. It defines the high-level structure of your whole application.
Okay, so there are 2 core rules. The first one, high-level modules should not depend on low-level modules. Both should depend on abstractions.
That's rule 1. And rule 2 just clarifies it. Abstractions should not depend on details. The details, the concrete implementations, should depend on the abstractions.
Wait, let's pause on that. That seems backwards. In normal programming, the high-level business logic uses the low-level stuff, right? My application uses the database driver. It depends on it.
That's why it's called inversion. The dependency arrow is flipped. In a conventional design, high-level code points directly at low-level code. Under DIP, both point inward toward an abstraction that the high-level code owns.
So the high-level business logic defines the contract, the interface.
Yes. And the volatile, low-level technical details, like a specific database or a third-party API, they have to implement that contract.
So if I change my database from, say, Postgres to MongoDB, my core business logic doesn't change at all.
Not a single line, because it only ever talks to the iDatabase connector interface that you defined. The low-level details are the ones that have to conform. You've decoupled them.
And the sources give that clear violation example with the switch and the light bulb.
Right. The bad example where the high-level switch class directly depends on the concrete low-level light bulb class.
If that switch is hard-coded to a light bulb, and then you want it to control a fan,
You're forced to modify the switch class, which violates DIP, and as you can see, it also violates OCP at the same time.
because you had to modify existing working code.
But if you introduce a switchable device interface, then the switch, the light bulb, and the fan all depend on that abstraction. The dependency is inverted. The system is stable.
So what does this all mean when we put the 5 principles together? S, O, L, I, and D.
Well, the collective purpose is really about architecting for change. These principles aren't just, academic ideas. They're the building blocks for code that is resilient, maintainable, and testable. They're how you achieve stability and reduce technical debt over the long haul.
They sound like architectural guardrails. They force you to think about the system as a structure of interconnected contracts, not just a list of instructions.
That's a perfect way to put it. Each letter tackles complexity from a different angle. SRP and ISP focus components and their contracts. LSP makes sure those contracts are trustworthy.
And then OCP and DIP give us the actual mechanism for stability.
And if you look closely, the underlying theme driving all of this is the pursuit of abstraction. It is. I think the core lesson to take away and explore further is this. Mastering that shift from concrete thinking to abstract thinking is what really separates good software engineers from great ones. By always seeking that abstraction, whether it's to define a responsibility, guarantee a contract, or manage a dependency, we ensure that the most valuable part of our system, the business logic, stays stable and protected. That becomes the reliable foundation for everything you build on top of it.